In this lesson, we're going to look at different properties of an area calculation. So if we look at the first example here, calculate the area of the shaded figure. Well, if you look at this figure, we can break it up into familiar shapes. We have a rectangle in the middle, and we've got two triangles. Labeling different aspects of these things. The rectangle has a side of 3 and 7. And then that side of 3 is also the base for the two triangles, which also happen to have an altitude of 3. So the first property of area is the fact that the area of a composite figure can be found by summing up or adding the areas of the figures that it's made up, that makes it up. There is no overlap, so we're just going to add the three areas together. So the area of the rectangle is going to be 3 times 7, which is 21. And then the area of one of the triangles is going to be 1/2 times 3 times 3. We happen to have two of those, though. So basically, if I multiply that by 2, that's going to reduce with the 1/2, and the area of the two triangles is going to be 9. So the total area is just the sum of the two. Plus 9 is going to be 30. And again, we determine that because we know that the total area is going to be the sum of the area of the rectangle plus the two triangles. So you just added them up because there is no overlap. Alright, the second example is a slightly different case. Here we have a triangle that is sitting on top of a rectangle, so there is overlap. And remember, when we have overlap, we're going to be subtracting away some things. If I want the area of the shaded region, it's like cutting this triangle out. So the second property of areas is that to find the area with areas can be subtracted if there is overlap to get the area of the shaded region. So on the outside we have the rectangle. So the area of the rectangle is going to be 21.6 times 12, and that ends up being 259.2. And then the area of the triangle, remember the area of a triangle is 1/2 base times height, and we're given the base and the height because the base and the height are always at 90 degrees from each other. So this is 1/2 times 9.6 times 7.2, and you calculate that ends up being 34.56. So the area of the shaded region is the area of the entire rectangle minus anything that is overlapping with the rectangles, and that's the triangle, 34.56. So this one is 224.64. That demonstrates the second property of areas is that they can be subtracted when you have overlap. Now, to deal with the sum of areas or the subtraction of areas, we have some terminology from set theory, and we're going to define some things so we can more formally talk about the adding of areas and the subtracting of areas. So first of all, to define a set is a collection of objects. In math, it's usually a collection of numbers, but it can be a collection of areas, or it can be a collection of really anything. And the objects that are collected are called members or elements of the set. And elements of a set are written with the braces, the fancy brackets. A subset, a set A is a subset of set B if every element of A is also an element of B. And here's the symbol for it. A is a subset of B. That's what this little sideways U is. The union of two sets is the combination of both things, everything that's in A and everything that's in B, all put together. So that's why we have a U here to represent the union. And then the intersection is what the two sets have in common. So they show up in both places. It's kind of where they think of an intersection. It's where they overlap. So intersection is the overlap. Union is where you're kind of adding all the areas together. The symbol for intersection is an upside down, is an N, an upside down N, a rounded N. So here's how these definitions work. This is a typical example using set theory. If I have set A 1, 2, 3, 5, 6 and set B is 2, 4, 6, 8, then A union B is everything in A and everything in B. Now we don't write the same number twice though, so we don't have to be redundant. Anything that shows up in either place is the union of A union B. So that's going to be 1, 2, 3, 4, it's supposed to be a 3, 3, 4, 5, 6, and 8. That's the union of A and B. Now the intersection of A and B is what they have in common. So if you look up here, they both have a 2 and they both have a 6. So the intersection of A and B is 2 and 6. It's what they have in common. Is A a subset of B? If A is to be a subset of B, then everything in A needs to show up in B. So clearly that's a no. Is B a subset of A? Everything in B has to show up in A. And again, we have things that don't. There's no 4 and there's no 8. So that's also a no. All right, let's look at the second example. D is 1, 2, 3, 4, 5. E is 1, 3, 5. D union E, if you look, it's just going to be set D again because everything is E, and E is up here. So D union E is just 1, 2, 3, 4, 5. D intersect E is going to be 1, 3, and 5. So D union E is just D. D intersect E is just E. Is D a subset of E? Is everything in D part of E? That's no. But is E a subset of D? That's yes, because everything here shows up in D. So that's a little introduction to set theory, and we use union and intersection when we talk about combining areas. So here's where we're going to use those symbols. I have two 2 by 2 square regions, and I don't know what that little, we just have to ignore that little guy. I'm not sure why he's there. Of S1 and S2, and they meet at the midpoints of the sides. So the overall length are 2 by 2. The outside lengths are 2. If they meet at the midpoints, that means this 2 is chopped in half, so the squares in the middle has a side length of 1. I want to find the area of the intersection of S1 and S2. The intersection is the overlap. It's going to be the area of the little square in the middle, because that's where the 2 overlap. Well, they both have a side length of 1, so the area of the intersection of the 2 squares is going to be 1 squared, and that's 1. Now we want to find the area of the union of the 2. That means I'm finding the area of this outside shape. Just like we don't list elements twice when you're finding the union, we also don't want to double dip when we do the area. So if to do this correctly, it's going to be the area of square 1 plus the area of square 2, but then we've got to subtract the area of their intersection. So that's how you write that in set theory form. So the area of square 1 and the area of square 2, they're both 2 squared. And then we already calculated that to be 1, so it's 4 plus 4 minus 1. The area of the union is 7. Now this example we're going to save for class. Or you can work on it, look at it on your own. I'll start labeling things though. 2 triangles, A, B, C, and D, E, F are shown, and they overlap, forming the center triangle there. Okay, and the altitudes are all given, so we're able to calculate the areas of the triangles. And then we have some dimensions down here. AD is going to be 4. AD is going to be 4. DC is going to be 3. And then CF is going to be 2. So we'll make that a different color. Make that purple. CF is 2. So from there, you want to figure out the area of the outside region, which would be this guy. So that's what we're going to do in class, is find the area of that guy. In the end, here's what we're doing, though. The area of the union of two regions is the sum of the areas minus the area of the intersection. So we don't count the overlapping part twice. That's what I was explaining before. So we'll do that one in class. Finally, we might get to, we have polygon regions that we don't have formulas for. So when that happens, what we would do is break the image up into shapes that we do recognize. So we would break up the image into regular shapes, the things that we do have formulas for. And then at the end, we'd have to add the areas together. So we'll do some more of this in class. You can start looking at this now, but we'll finish it up in class. You can draw lines to figure out how you can divide those polygonal regions so we can easily calculate areas.